we're going to turn our attention to tangent planes and the concept of level surfaces. If a surface has an equation f of x, y, z equals k, a constant, then it can be considered a level surface of f. When we talk about level surface, that may bring to mind a level curve in R2, and that's exactly what this is like, except it's the 3D analog. And just to give you something to wrap your mind around here, if our function f is equal to x squared plus y squared plus z squared, then various values of k would indicate a sphere of various radii, you see. Each of those spheres would be considered a level surface of the function f. So that's where we are here. We can describe a curve on S, and I just realized I should have said if a surface S has an equation f of x, y, z equals k. Now, we can describe a curve on S using a vector function, r of t, which is given by x of t, y of t, z of t. Replacing x of t, y of t, and z of t as the arguments of f, the surface S becomes f of x of t, y of t, z of t equals k. If the component functions x, y, and z are differentiable, then finding the derivative using the chain rule, partial of f with respect to x times dx dt, and then so on for y and z, adding them together, equals 0. Well, we can express this as del f dot r prime of t is equal to 0, which means that the gradient vector del f is orthogonal to the tangent vector r prime of t at any point x naught, y naught, z naught. What we end up with is the equation of the tangent plane to the level surface S at the point x naught, y naught, z naught is fx of x naught, y naught, z naught times x minus x naught plus the partial with respect to y at x naught, y naught, z naught times y minus y naught plus the partial with respect to z at x naught, y naught, z naught times z minus z naught, using the equation that we've seen before of a plane. Visually, we can represent this using what works out to be, it's my favorite picture in R3, just this little, sheet of a surface that we're saying has equation f of x, y, z equals k. Now, the idea here is we have a curve on the surface S, and we're considering a point on that curve. Associated with that point is a tangent line. Let's see, maybe it looks like it's about right there. I said tangent line and I meant tangent vector r prime. Now the tail of r prime is a point on the curve. It's also on the surface. The curve is given by r of t, and we'll say that this is r of t naught for some fixed point here. And it has its tip at the point x naught, y naught, z naught. Now the normal vector for the surface is what gives us the normal vector for the plane. And it's orthogonal to r prime. It is del f. So a surface on which is a curve. There's a point on the curve. It's r prime of t naught. At that point, there's a tangent vector r prime. Orthogonal to r prime is the gradient vector del f. And because it's orthogonal to the tangent, it's orthogonal to the plane that contains the tangent vector, and so its components become the coefficients of the plane. Now there's a line that contains del f. It goes through the point on the curve, which is on the surface, and it's parallel to f, and it's called the normal line to S. And we can say that the normal line to S at the point x naught, y naught, z naught is x minus x naught divided by fx, the partial, at x naught, y naught, z naught equals y minus y naught divided by fy, the partial, at x naught, y naught, z naught, and that equals z minus z naught divided by fz at x naught, y naught, z naught. And I've chosen to give these to you as symmetric equations. This can be applied to a function of two variables. We construct a function f of x, y, z as, so that's uppercase f, as lowercase f of x, y. So we're just denoting what space we're in, right? So minus z is equal to 0. Then uppercase f x at x naught, y naught, z naught becomes lowercase f x at x naught, y naught. Likewise for the partial with respect to y. The partial with respect to z at x naught, y naught, z naught for uppercase f is then -1. Then the equation of the tangent plane is lowercase f x, that partial with at x naught, y naught, times x minus x naught plus fy at x naught, y naught times y minus y naught minus the quantity of z minus z naught equals 0. And you'll see that this fits very well with the equation of the tangent plane that we saw before. We're going to close out with a quick example. We're going to find equations of the tangent plane and the normal line to the surface x equals y squared plus z squared plus 1 at the point 3, 1, -1. First things first, our surface is going to be written as y squared plus z squared minus x equals -1. We need all the variables on one side and the constant on the other. Remember, we were looking at this through the lens of f of x, y, z is equal to k. With that in mind, I'd like for you to pause the video and go ahead and come up with the equations of the tangent plane and the normal line. Del f is going to be -1, 2y, 2z. So del f at 3, 1, -1 is -1, 2, -1, excuse me there. So the tangent plane has those as coefficients, and then the point is 3, 1, -1. So -1 times the quantity of x minus 3 plus 2 times the quantity of y minus 1 minus 2 times the quantity of z plus 1 is equal to 0. That simplifies to x minus 2y plus 2z is equal to 1. The normal line is, we can actually use the numbers that you see in the equation of the tangent plane. X minus 3 divided by -1 equals y minus 1 divided by 2, which equals z plus 1 divided by -2. That's for the symmetric equations. If you decided to go with parametric equations, you would have said x equals 3 minus t, y equals 1 plus 2t, and z equals -1 minus 2t. I encourage you to, after you've taken all this down, look at GeoGebra, graph the surface, as well as the plane and the normal line so that you can see how all this works together.